Hey there students, Mr. Fugit here. In our video today, we're going to spend a little bit of time setting up how we're going to be approaching Lab 4D titled Use the Force. So as usual for our lab activities, you'll want to make sure you can access the lab assignment on Canvas. So depending on the year in which you're watching this video, you'll want to navigate on Canvas down to our Week at a Glance page and then make sure to locate the appropriate day. You should see something in there labeled Lab 4D Deliverable, and it should be titled Use the Force. From there, as usual, you should be able to make your copy of our lab document so you have this document to work with. You will need the document because it's going to give us some context, instruction, tables with which we can collect our data. We'll make sure we need our document. So I'm going to assume that in our discussion, you've already made your copy of the document. If you haven't, pause the video now, go get your copy so you can read through things with me here. So here's what we've got for our lab today. It says this: today we will be working with a pullback or wind-up car, a little bit of a different mechanism than the cars we dealt with in some of our previous labs. This is actually what we have for today. It's actually a pullback or wind-up car, except we've taken the body of the car off. We just have what we would call the frame or the chassis left. Hey, now, it still functions the same way the other cars would. I can pull the car back, let it go. It's just much lighter. And we'll kind of get into a little bit of why we did that a little bit later on. Now, it says this: the car will start from rest. That's going to be an important data point that we will need for a part of our analysis later, and speed up as it moves a distance of 1 meter. So eventually what you're going to be doing is this: taking your car and pulling it back a set distance, because we do want to make sure we control that so our trials are relatively consistent. We're going to pull our car back, and then we're going to time how long it takes the car to travel a meter. Just to give us a little bit of context. And we'll do a demo with that here in just a moment. So the car does this because of a spring-loaded system. Effectively, as I pull the car back, it's compressing a spring, and then when I release it, lets the spring go, and the car begins to travel forward. So there is going to be an acceleration here, and that's going to be a part of what we focus on. Remember, acceleration is just a change in our motion, specifically a change in our velocity. So it says this: the force supplied by that spring should stay about the same if we set up the car the same way each time. What we mean by that is this: as long as I'm pulling the car back by the same distance every time, I should get a relatively constant force being applied onto the car. Now, that force is going to change if I pull it back by a farther distance or a shorter distance. So that's a variable that we want to make sure we try and control, pulling back our car by the same distance each time. So, moving on, it says this: using this mostly, again, we're kind of assuming that here, mostly constant force, we can see how changing the mass of our car affects our acceleration. So this is going to be the relationship that we focus on in our lab today, the relationship of mass to acceleration when we have a relatively constant force. Newton's second law states that mass and acceleration have an inversely proportional relationship. We're going to collect some data and see if it agrees with this prediction. That's going to be our focus for today. We're going to try to take some data to see how changing the mass of our object changes our object's acceleration, assuming we have a constant force. So to give us a little bit of context, and we're going to do a demo of this here in just a moment. Come to a new page here. Sorry about that. Here's what Newton's second law states: the sum of forces acting on an object should be equal to the object's mass multiplied by its acceleration. Now, to keep things relatively simple, let's say we've got our wind-up car here, and we've got a force, right? We pull back the car, we release it, and then the car is going to accelerate forward. So there's going to be some force propelling the car forward, right? I may call that like a push force, right? Something inside the car's mechanism is going to help push the car forward. I'll just call it a push force. Now, are there other forces acting on the object? Maybe, but we're going to simplify things and say, for now, this is the only force we're really going to be analyzing, the force from, well, the spring-loaded mechanism that helps push our car forward. And we're going to say that that force is mostly constant. So we're going to assume that there's one force acting on our object, even though there may actually be more. We'll talk about that later. We're going to assume that there's one force acting on our car. And we're going to assume that that one force is constant. So what we're going to be doing is, assuming that our force is constant, we're going to see how changing our mass, we're going to be adding increasing amounts of mass to our car. We're going to see how increasing our mass affects our acceleration. If we increase our mass, we add more and more mass to our car, what is that going to do to the acceleration of our car? What Newton's second law says should happen is this. If this is constant, meaning this side of my equation doesn't change, that means the product of this side of my equation doesn't change. And if this is constant, the product over here should also be constant. But if I'm changing one of my terms, if mass goes up, but mass times acceleration has to be a constant, Newton's second law actually states that our acceleration should go down. Right? Because the product of those two things, m times a, would have to be a constant value. And if mass is going up, Newton's second law predicts that our acceleration should go down, which means that as we add more and more mass, we should see a lower and lower and lower acceleration. Now, that's what Newton's second law tells us should happen. We don't just want to take that as fact. We want to try and verify that, validate that prediction. That's part of what we're going to try to focus on today. If this is what Newton's second law says should happen, does that agree with what's actually happening in the real world? Remember, as we talked about quite often with Isaac Newton, our goal here is to use mathematical models, to use math as a way of understanding the physical world. That's what we're trying to do here. Collect data, do some analysis to see if this relationship actually holds up in the physical world. So that's going to be our goal. Now, as you look back at your lab sheet, there's a lot of information, a lot of things that are going on here. What I want to draw your attention to is this. Okay? There are some instructions, and we're going to walk through a little bit of what's going on there. Okay? And in short, we're going to need to collect two main pieces of data. The mass of our object, which is relatively straightforward. All we need is something like a scale. We can place our objects on the scale and get a reading on mass. That's not a very hard thing for us to get. However, acceleration, that can be a little bit more challenging. We don't have a tool that can help us get an acceleration value. And that's where a little bit of what we know about kinematics is going to come into play. Hence, our meter stick. All right, if our car starts from rest, travels a distance of 1 meter, we could maybe even record the time it takes to do so, and then we could use that to work with a kinematic equation. To give you a little bit of a clue, here's what I would suggest doing. Board seems to be responding a little bit slow. Sorry about that. What we may consider doing is something like this. Well, if we measure our delta x, as long as we make sure our car is traveling 1 meter, we know that the car is going to start from rest, so initial velocity would be 0 meters per second. We don't really know the final velocity, meaning we don't know how fast the car is going to be moving after it travels the 1 meter, nor do we really care about that number here. Acceleration, we do care about, so I'll put a star by that. That's the term we want. And then time, even though we don't love doing this, we can, in fact, measure our time. It's probably not the absolute best way to find our acceleration, but it's a decent way. And hopefully we're dealing with something that takes, well, at least maybe a second or so to occur. So if our times aren't terribly small, then recording time's not that bad of a way to go about doing this, right? We really want to avoid measuring time if something that we're looking at happens very quickly, like a few tenths of a second. But if we're looking at something that happens over the course of 2, 3, 4, 5 seconds, measuring time is not that bad of an approach because our times are a little bit bigger for us to get. So once I know this stuff, I'll put a check by time, meaning I know that, I should be able to use an equation to find this, right, my acceleration. Really the equation without v1, which we've used quite a bit. I'll leave that up to you all to decide. But hopefully this gives us a rough idea on what we're trying to do here. We're going to take our car, measure the time it takes to travel 1 meter, use what we know about kinematics to find the car's acceleration, and then we're basically going to set up, well, kind of a chart. Mass versus acceleration. Mass of our object versus the acceleration of our object. And then we're going to begin to look at that relationship. We're actually going to generate a graph of mass versus acceleration and see what happens. Do our numbers actually agree with what Newton's second law says should happen? Is there actually an inverse relationship? Greater mass, lower acceleration? Does that actually hold up to be true? That's what we're trying to validate here. Does Newton's second law actually fit what happens in the physical world when we start to take some numbers and analyze them? So that's a bit of an overview on what we're trying to do here in our lab. I'm going to transition over now and show you a little bit of how our setup should look. That way, if you're doing this remotely or if you're doing this, well, kind of on your own and want a good idea on what's going on, you have a good idea of what we're doing here. But hopefully this gives us a good setup. We're going to transition over now and look at how this will look in actual practice. Okay, so here's my rough setup here. I've got my pullback car right here. Hopefully you all can see things okay. I've got my meter stick just to make sure I'm working with 1 meter of space here. And I've got a few masses. You're actually going to have a whole set of masses. I just have a few here. I'm not going to go through and collect all of the data. but I will show you roughly how things are going to work. Okay, so I've got my, well, kind of car frame here. Now you'll notice on your car there's going to be a bolt here at the front. That bolt is there to actually allow our masses to clip onto what we're doing. Right? So each of the masses that you deal with should have a binder clip on them. Please, please, please make sure you do not take that binder clip off. These masses were actually made by myself or by your instructor, your other instructor, which is probably Sanchez. He has a set somewhat similar to this. I actually got the idea from him, so kudos to you, Sanchez. But the masses are actually made in such a way that all the things on here together should add up to the mass that you're working with. This says 200 grams. So if you take the binder clip off, it's actually changing the mass, and this is no longer 200 grams. There's also a functional purpose to the binder clips. Here, we're going to be able to use that to clip into our... We're going to use them to be able to clip into our bolt. And that way the masses hopefully won't fall off or jostle around. So now when I pull my car back and I let it go, my mass is going to stay relatively stationary. That's one of the functional reasons we actually decided to take the bodies off of the cars, was because the masses tended to jostle around a whole lot. So please do make sure that when you're working with these to leave the binder clips in fact on devices. So I'm going to make a little adjustment here. I can actually work this around. Sorry about that. This should be, oh, no, I think this is good to go. Okay, so a couple of things that we want to make sure we go over. We said that the force on the car should remain relatively constant. That's as long as we are actually setting up our car the same way each time. So if you look at the instructions in your lab, what you'll see is we want to make sure we pull the car back by about the same distance every time. So I'm going to take the front end of my car, right, because I want to measure a meter from front end here to front end here. So I make sure the front end of the car travels 1 full meter. Technically, we could go back end to back end, but seeing the front end is a little bit easier because it's what we see first. So I'm going to start with the front end at right about 40 centimeters. I'm going to try to be as exact as I can. I'm going to take my car all the way back till the front end is right here at 0 meters. Now, at this point, I'm going to get my timer ready. There we go. So that when I give it 3, 2, 1, I can go 3, 2, 1, start, and then stop whenever the car reaches the end of that 1 meter. Now, there's a few ways to do this. I have over here one of my just hoodies set up. It's a little bit cold today, so I had a hoodie with me. But I've got my hoodie set up as a way to kind of barricade the car after it travels the 1 meter. I would suggest having something at the end of your meter stick. That way it doesn't just fly off of the table. These aren't horribly expensive, but we still want to be very careful with them because they weren't free. So please do be careful when you're working with these. Have something set up here, maybe a jacket, even like a book bag, something that's going to kind of soften the impact. Now, in terms of collecting your data, that's how we're going to get our times, right? We're going to start whenever we release the car, and then we're going to stop whenever the car reaches the end of the 1 meter stick. Now, it's kind of up to you all how you decide to have people perform different roles here. I will say one thing that can be kind of nice is whoever you have releasing the car, you might also want to have that person be the timer, because they're going to be able to know exactly when their hand comes off and exactly when to start the timer. So again, I'll show you that again. Start at 40, pull your car back, right? Timer at 0, 3, 2, 1, start, stop. Right, now, again, when there's no mass on here, the car's going to be going relatively quickly. So that first data point is going to be kind of tough to get. So you may even consider having more than one person recording time. You should probably have a group of at least 3 or 4 people here, so you could have more than one person recording that. Okay? So that's roughly what we're going to do. Now, eventually, what we're going to do is we're going to begin to add mass. So I'll take, this here is my 50 gram mass. I would take my binder clip that onto the bolt. Okay? So it should be relatively secure. And then, again, I would do the same thing. I would start at 40 centimeters. Now, one thing you do want to be careful of is here, you'll notice there's a bit of a series of, well, cogs, kind of gears, if you will. You want to make sure your masses aren't rubbing against those, because that kind of ends up being what turns the spring in here. So we want to be careful there. I'll try to adjust that as well as I can. So 40 centimeters. I go back all the way to 0. And then again, get my timer ready. 3, 2, 1, start. And stop. Now you will notice that the car might accelerate a little bit differently. So that's again going to be evidence that changing the mass does have an effect on the acceleration. So as we've talked about many times, we want to make sure we try and reduce error in doing this, meaning we probably want to collect our data at least a few times at every different mass setting. So you'll want to do this at least 3 times at each setting so that we get a pretty good idea of our time. As we talk about very often, time is not the most reliable thing for us to measure because it involves us reacting to whatever stimulus we see, right, where the car is at different points in time. Especially if I'm all the way over here, I'm not going to be able to see the ending point very clearly. So in fact, if I'm doing this, I may actually want to stand up so I can see my starting and ending points a little bit more clearly. Again, your analysis here is really only going to be as good as the data that we have, so we want to try to be as accurate as we can with our data. So you'll have your set of masses, you'll clip each of those masses, again, into your bolt, get them set up onto your car, trying to avoid that gear mechanism. Bring things back, and then again, just so we're clear, 3, 2, 1, start. And then stop whenever it reaches the end of that 1 meter. If the car does end up hitting the meter stick at any point, we probably want to recollect that data point because if we hit the car or if we hit the meter stick, that's going to introduce a force that could change what's happening with our acceleration. So we want to try to make sure the car doesn't hit anything as it travels that full 1 meter. And then once we have all of our times, we should be able to use those as we talked about earlier with our kinematic equation to get our acceleration. And then that should be able to give us what we need, mass and acceleration, as a way to verify what's happening here with Newton's second law. Now, in terms of the analysis, we're going to spend some time talking through that in class. So don't stress too much on all the analysis. It is relatively straightforward, laid out in your lab, but we are going to spend some time talking through what our numbers should look like, what they do look like, and how they maybe verify or can help us explain what's going on there with Newton's second law. So hopefully that gives us a pretty good overview as to what we're doing here in Lab 4D. As always, if you have any questions, please make sure to communicate them to your instructor. We would be more than happy to address those. Other than that, good luck.